teach Steepest Descent with you watching my video, and I'm not sure it's the best way, or I hate to see myself on video, but we're going to try it anyway. So the goal is to minimize functions. We have a function f. We assume it depends on the parameters theta, which is a vector, and we want to find the minimum of this function. So we will write it like minimize over theta of f of theta, where theta is a vector. So theta here can be a vector that looks like this, theta 1 up to theta n. This is what we're going to try to do, and we're going to try to minimize and talk about the solution of these things. So in 2 dimension, if you want to think about it for a second, you think about function theta, which is, let's say, theta 1 and theta 2, and you have a function f, which has some contours. And your goal is to somehow get from a starting point here that you guess where theta is, to somehow get to the minimum, which in this case may be here. So you're attempting to find a path that would lead you from the initial theta, which is let's call this thing theta 0, to some star, theta star, which is going to be here, which we are going to assume it's at the minimum of the function, theta star. That's basically what we're going to try to do in this particular class. The fact we want to minimize a function, the next question is, how do we actually do it? So if you learn calculus, you would know that one way to do this is would say, if I want to minimize f of theta, I will basically compute the gradient of f with respect to theta and make it equal to 0. And then try to solve this equation. The problem is that for general function, we can't really do this because the solution of a nonlinear system of equation is not a closed form. So that cannot be done in general. What we're going to do is we're going to have a new concept here, and the concept is a concept of an iterative procedure. An iterative procedure is not giving you the answer in one shot. An iterative procedure basically says that we're going to improve our situation slowly but surely, and at the end of the day, when we finish improving our situation, we will be at the minimum. So you can think about it from a point of view of graphical thing, that you're here at some theta 0 that you want to approach and you want to get to here. You're not going to get from here to here in one go. What you're going to do is you're going to take steps somehow, and these steps eventually would lead you over here. To be honest, it could be that most of the time, the number of steps that need to get you all the way to the end is infinity. However, after a finite number of steps, you'll be close enough for all practical purposes to the solution of the minimum. So we are going to think about what we call an iterative process, so an iteration, where we're going to have something which looks like this. We're going to have theta j plus 1 will be equal to theta j plus some mu times sj, where sj is going to be a direction, and mu is going to be some how far we're actually going in that direction. So you can think about it graphically. This is the first s, this is s1, and mu is the length of this, and this is going to be s2, and u is the length of it, and so on until I converge to where I want to be. And that's the way we're going to get to the whole thing. We're going to have an iterative process like this, where theta j, the limit, as j goes to infinity, we don't really have to go and all these kind of things, will equal to theta star. That's what we really want to have. We want to go ahead and to have an iterative process like this, that when it's all done, it's converging. And that's the concept of we talked about this idea of an iterative procedure where we take the next point to be the point we have right now, plus some step length, plus some direction. And the real question, there are 2 questions really. How do we compute the direction, and how do we compute the step length? So let me start with talking about how we compute the direction of what we have. The basic idea is this. If I'm thinking about the function that I want to minimize, it's going to be f of theta, and at point j is going to be f of theta j. And what I want is, I want the function at theta j plus 1 to be smaller than the function of theta j. Is to find a direction such that the new function, the new point, is going to be smaller than the function of the old point. So the question is how we do that. And that's actually relatively straightforward. I'm going to rewrite this thing again, and I'm going to use the tool that is most commonly used when you do numerical optimization, and that's Taylor's expansion. So what we're going to do is we're going to write it like this. We're going to write f of theta j is going to be, has to be larger than f of theta j plus 1. But what is theta j plus 1? Well, theta j plus 1 is going to be equal to f of theta j plus the gradient of theta of f at theta j transpose times delta theta, where delta theta is the parameters we have here, or if you want to think about it, I'm going to replace delta theta with s here. Now I'm add higher order terms. So if the step we're taking is small enough, I can ignore these and basically say that this is just equal to this thing. So what can I get from here? I can get here the following thing. I can now ignore for a second this step and just look at this one. I will subtract f of theta j from both sides and get that what I need to have is that the gradient of f at point theta j transpose times s have to be smaller than 0. So that is telling me something about s. The inner product with s and the gradient of f have to be smaller than 0, and I can pick any, in principle, any s such that this condition holds. However, an easiest one to pick is to say s is going to be equal to minus the gradient of f at point theta j, which immediately tells me that this thing is going to be smaller than 0. Now you can think about it graphically. Again, if I think about my function, I'm here, the gradient of f wants to take you here, and then the minus gradient leads you over here, and then any direction, s can be any direction that is in this point that the inner product between, so this is gradient of f, this is minus gradient of f, and any direction in here is going to be okay. Of course, the best direction that leads you down is the one that is gradient of f, and that's going to give you the step of the most descent, locally at least, when you're here, and that's called the steepest descent direction. So this is the steepest descent direction. About is how to pick mu and how to come up with an algorithm. And there are basically two approaches to come with mu. One is to have an adaptive way to do it, which I'm not going to cover right now. I'm going to talk about the simplest option, which is just choosing something. And choosing something is not a real science somehow, but we'll talk a second about it. So the idea we have is this. Remember, s was supposed to be equal to the minus gradient of f at theta j. So basically we have an algorithm that says something like this. For I is equal 1 to whatever, update theta j plus 1 is going to be equal to theta j minus mu j gradient f of theta j. And that's basically the steepest descent algorithm. And again, I have to choose mu. Now, the thing is that mu, I can have it as choices to make sure that the function decreases, but many algorithms just says, I want to, for simplicity, choose mu to be constant. Now remember that mu came from this idea that the Taylor expansion really holds. So if I think about Taylor expansion, once again, is coming from f of theta plus mu s is going to be equal to f of theta plus mu times grad f transpose s plus mu square over 2 grad f Hessian of s, and actually I'm going to write an expression here which is not so important here. This is a much more complicated expression. The important thing is that this is mu square here, multiplied by mu square. So if we want to ignore this term, we have to make sure that mu is small enough such that this term is small compared to basically this one. Now, if we take s, if we normalize s, if we say, let's say that we want to make sure that this is not too large, then we can go ahead and make sure that this is smaller. So practically speaking, people are looking at the gradient of f and saying, let's make this whole term really small enough. So for example, a common choice for mu will be 0.01 or 0.1, depends on the problem. There is no really set example to set number I can give you, but if the gradient of f is going to be on order 1, for example, setting mu to be 10 to the minus 2 will be reasonable. There is a much more sciencey way to answer this, and we will do this next time. But right now, for a very simple thing, an algorithm that basically require one line, is you choose mu to be small enough. So you say mu j is equal mu small. And you can start playing with that and see how this behaves. In many cases, people try a bunch of mu's to see how it behaves. But again, we will talk about how to choose mu in a more scientific way in the next time. And that basically summarizes what we have done for steepest descent. The next thing is for you to start coding it.